Ready to go? Okay, thank you. So welcome back from lunch. I hope you had a nice break. So I'm Stuart Bolton, as I was introduced this morning. I wanted to spend just a couple of minutes doing a little bit of promotion here and show you a little bit about the Herrick Labs where I am working. The Herrick Labs is part, and you can find this all on the website shown here, but the Herrick Labs is part of mechanical engineering at Purdue University, but physically separate. It's maybe almost a kilometer away from the main building. It was founded in 1957 by one of our professors, a fellow Bill Fontaine, who was interested in doing work that was of interest to industry, which was a little bit unusual for universities at that time to be doing sort of applied research. The funding for the lab, maybe not surprisingly, came from Ray W. Herrick, who ran a company called Tecumseh Products, which made compressors for refrigerators and also two-stroke engines for things like lawn mowers and other small devices. And Bill Fontaine managed to convince Ray Herrick to part with $250,000, which in 1956 was a lot of money. But the university then gave Bill an old barn that was built in 1912, actually. But Bill took the money he'd been given to build some new wings on the building. And that building still exists today. However, we have since then moved to a new building, which opened, well, let's try that again, which opened just a couple of years ago. With the result of some funding from the National Institutes of Standards and Technology through an infrastructure project. So this was a $30 million project which replaced about 2/3 of the activities of the old lab and, of course, includes some new space as well. So these days we have the new building, which houses mostly heating and ventilating, thermal systems, and engines work, whereas the poor acoustics people still live in the old building, right? So we're looking for, a small advertisement here, we're looking for $15 million to rebuild the acoustics facility. So I hope you play the lottery. And we will be happy to consider naming opportunities, as we say, for you. But just to give you a small flavor of what goes on, you can see there's thermal systems and HVAC, mostly relatively big systems from whole buildings down to component rooftop chillers and things like that. Patricia, the director of the lab, Patricia Davis, is interested in perception-based engineering, which has to do with including, let's say, human aspects in the design process so that you can design to particular human-based outcomes rather than just numerical things. So the lab itself is built to do a lot of psychophysics testing, multimodal testing involving exposure to sound and vibration at the same time, for example. There's a lot of engines work that is sponsored mostly by Cummins engines, and as a result we actually have fairly close ties with the Women's College in Pune, which was funded by Cummins, I believe, or the Cummins Foundation. As well as, of course, the historic acoustics, noise and vibration stuff, which I'm a part of. Excuse me. We have the kind of normal facilities that are of use in the acoustics world, so anechoic chamber, reverberation room, hemianechoic, a large hemianechoic room, as well as the audiometric booth, which is shown up here, that we use for subjective testing and building up models of human response to various types of sounds. One particular device that is of use to us is something called the tire pavement test apparatus, which allows us to run real tires on real road surfaces. You can't quite see it here, but the tire is mounted horizontally and runs around on this concrete surface at speeds up to 50 kilometers per hour with microphones going along with the tire so that you can measure the noise being radiated from the contact patch and things. So it's a very useful tool for looking at tire noise in a laboratory environment, which is also a bit unusual. Search here. If you do a search for the publications of the Ray W. Herrick laboratories, you will find large numbers of conference publications, actually mostly by me, I have to admit, because I have an interest in this site. But these are most of the conference publications that we've done in recent years. And for historical purposes, in fact, this goes all the way back to my very first conference presentation in 1977. How many years ago was that, right? So, but anyway, so you can amuse yourself by taking a look at various things, including, let's see what the most recent stuff is. So I'll talk a little bit about this on Friday, but for example, this is, okay, sorry, that one is not available. Oh, okay, that's going to take a little while. But anyway, so if you have a moment, though, you can browse through that and get some sense of what the work is that we've been doing recently in various areas. But in the meantime, let's get back to this. So the objective here is to talk a little bit about basic aspects of sound, in particular the physical aspects, without, I'm afraid, using too many equations. There are a few, right? Also, you can take a look at the notes that have been distributed, which give perhaps a little bit more technical detail than I will be going into here. So let's get underway. So, of course, we're interested in noise from a number of points of view, but mostly noise viewed as unwanted sound, and from a variety of sources here, transportation, appliances, and so on and so forth, which cause some annoyance, for example. So why is acoustic noise a problem? Of course, there is increasing mechanization of a lot of things. In the part of the reason this course was delayed in the fall or in the autumn, I was in hospital for a while, and if you've been in hospital, you'll know that there are very many machines that make a lot of noise, right? So, so sleep is a bit of an issue in that case. Cities are becoming more crowded. Of course, I don't need to tell you that, but there are many big cities where noise is an issue. Environmental noise, of course, with increased transportation, lots of air traffic, and so on and so forth. And of course, there's a commercial incentive involving, let's say, the global marketplace down here, since often products are judged, or their quality is in part judged based on the sound that they make, right? So that if you want to be competitive in the marketplace in some respects, you need to pay attention to what your product sounds like. So the consequences of noise exposure, again, this is not too surprising, but we've often thought that the major consequence of noise exposure was noise-induced hearing loss, so physical damage to the hair cells in the ear, which limit your ability to hear, right? And certainly as you get older, this becomes more of an issue. But beyond the sort of physical impact of hearing loss, there are other issues, speech interference, for example, so limiting communication ability in noisy spaces, which may be unsafe if you cannot communicate effectively with your colleagues. There's, of course, annoyance, which is not generally a good thing. You don't want to increase your stress levels. And then there's increasing evidence of substantial health effects that are not related specifically to hearing, but specifically raised blood pressure from sleep disturbance. It's now understood that even if noise does not wake you up at night, noise exposure will temporarily raise your blood pressure and also change sleep states. So that your sleep is not as effective, and the long-term effect can be heart disease of various kinds, and of course fatigue and various other things. So there's now substantial evidence that there's increased mortality rates near airports, for example, in the long term, simply because of noise exposure. And there's some thought that there may be as much early mortality due to noise exposure as there is due to traffic accidents, for example. So we pay a lot of attention to safety in vehicles with seat belts, various other devices, but maybe not so much to our hearing, which also deserves some respect. So noise control is interesting because it combines a number of different disciplines into one. Of course, acoustics is an important part of noise control, being able to understand how sound propagates, how it's generated. But beyond that, you need to take the human into account, as Professor Mohanty was saying this morning, because ultimately that's our objective, I think, as noise control engineers, to keep sound under control so as not to disturb the environment or people. And that is why noise control is actually difficult, I would say. I tell people that acoustics is easy, right? Anybody can do acoustics. There's always an acoustical solution. If you have a noise problem, you can always put a box over it, or you can put lead sheets around it or something. But in the real world, of course, people want you to achieve that result without it costing anything, without giving you any space to work with, and of course no weight, right? And any solution that you come up with is meant to last for 20 years without maintenance. And those are the kind of functional attributes that make noise control difficult, right? So if they would let us put lead on aircraft, for example, it would be easy, but for some reason they won't let us do that, right? So that's where some of the challenges come in. So in this lecture, I want to talk just about the very basics here, the things that we look at from an acoustical point of view: sound pressure, particle velocity, acoustic intensity, and sound power. So these are the fundamental quantities that we're concerned with sound, and we'll say a few words about these and why they might be useful. So acoustics, which is the study of small amplitude pressure disturbances which propagate in an elastic medium. So that covers a broad range of things, including wave propagation in solids, underwater, and so on and so forth. From a noise control point of view, we're usually concerned maybe with what you might refer to as sound, which is airborne acoustic signatures that we can hear. So typically from 20 hertz to 20 kilohertz, or if you're my age, probably 20 hertz to 8 kilohertz or something. But we're usually concerned with audio things that we can hear. As mentioned this morning, sound pressure is a very small disturbance that rides on top of atmospheric pressure, right? So we are surrounded by an atmosphere that presents a pressure of about 1 times 10 to the 5th pascals at sea level, whereas the fluctuating sound, the little ripple that rides on top of that, is 5 orders of magnitude smaller than the ambient pressure. And so 1 Pascal, I don't know if anyone has any experience with decibels, do you know what 1 Pascal corresponds to? An RMS pressure of 1 Pascal in decibels is? This is a figure that not quite. No, so 1 Pascal, RMS pressure of 1 Pascal corresponds to 94 decibels, right? So that's a pretty loud sound, right, for a pressure that's pretty small. And as we'll see later, the ear is an amazing transducer because it can cope with sound pressures from multiple tens of pascals down to essentially micropascals, right? So huge dynamic range that we are dealing with. One of the things that does actually make acoustics a little bit easy from a theoretical point of view is simply the fact that the sound pressures are pretty small compared to ambient pressures. And so that lets us make a number of approximations when deriving wave equations and things. And perhaps most importantly, from a theoretical point of view, it lets us operate in this linear acoustics world where if you've got 2 machines or 2 sources making noise, you can simply add the noises from the 2 machines to give you the total noise. So a very simple addition process to add up various sources to give you a total sound field. And that is what linear acoustics refers to and what, again, makes our life a little bit easy. When we're deriving wave equations and things, in the normal circumstance, we would make a large number of assumptions, again, to make our life easy, but which in fact are pretty realistic. The first one, of course, that the pressure is small, the fluctuating pressure is small compared to ambient, but also assuming for the moment that the air is not moving, that the medium is stationary, which works, the rule of thumb is that works okay up to some fraction of the speed of sound in air. So maybe if we say 20 meters per second, that's fairly fast for airflows in HVAC systems, for example. But as far as the sound field is concerned, we can still say that the medium is stationary. We all, also say the medium's an ideal gas, and that viscous effects are negligible, so that we don't have to account for viscous interaction with surfaces, for example, which again would make life a little bit difficult. Some numbers that I think most acoustics people remember is, of course, the density of air is important, 1.2 kilograms per meter cubed. I was going to say meter squared there. And then the speed of sound, 340 meters per second, which is at essentially room temperature. The atmospheric pressure, 1 times 10 to the 5th pascals, and then characteristic impedance, the relation between particle velocity and pressure in a propagating plane wave is this 415 MKS rails, right? And we will come back to that one as well. So if you generate a wave equation, right, and look, then it's a second order partial differential equation, but do the solution of that, we'll see that there are two components to the solution. In a plane wave case, one solution involves something traveling in one direction, the other solution involves something traveling in the other direction. And so the fact that the solutions represent something that's propagating or traveling is why it's referred to as the wave equation. And let's say another important consequence of the linearity of the problem is that signals propagate without changing their shape. Right, so that in this little illustration, we have a little pulse of sound here at t equals 0 seconds that's propagating to the right, and 1 second later, it's traveled 340 meters per second, but 340 meters, but it still has the same shape, right? And this is very important to us from a, let's say, human point of view, because this is what allows us to communicate, right? That essentially the information that is leaving my mouth arrives at your ears in a more or less undistorted form, right? So if there were nonlinear effects, or if there was dispersion where different frequency components travel at different speeds, then it would actually be very difficult for us to communicate. So fortunately, we live in a world where linear acoustics applies, and so we can communicate effectively with each other sometimes. Right? I think there's a psychological aspect to that, but the physics is under control. So the wave equation in one dimension is shown here. You can arrive at this point as illustrated in the course notes by combining equations of state, relations between pressure and density, as well as dynamic equations, essentially Newton's second law, force equals mass times acceleration, applied to little chunks of fluid. And you end up with this, this equation here, which relates this variable, which could be the sound pressure, to what this is basically saying is that the curvature of a wavefront, or the curvature of a wave, is balanced by the the rate of change of the pressure, the second derivative of the pressure with respect to time, right? So time rate of change of pressure. And the solution of that, as many of you know, I think, is expressed in this form. The pressure as a function of position and time is equal to a sum of two components, right? And these functions can be any shapes at all. So there's no restriction on the shape of this thing. So anything so long as the amplitude is still in linear range. But the variables here, xi and eta, actually represent combinations of space and time, right? So this eta t minus x over c naught, xi is t minus x over c naught, eta t plus x over c naught. If you take a look at this one for a moment and ask yourself what this means, right? You follow a point on the wave, right? This is a wave function here. And you can follow a particular point on the wave as time changes by keeping the value of xi constant, right? So if you want to keep this quantity constant, but t is increasing, that means that x has to increase as well, right, to maintain the same value. By the same token, this one, if you let t advance, but you want eta to maintain the same value, x has to get smaller, right? So this means that this represents something that is maintaining its shape, but is propagating to the right, or the positive x direction, whereas this one is maintaining its shape, but propagating to the left, right? So in one dimension, the total solution of the wave equation involves something propagating this way and something propagating this way, and these two things can interfere with each other to create the total sound field that we experience. So the simplest type of sound wave, say, is something that is simple harmonic, so pure tone, single frequency component oscillating with time. You're familiar with these concepts that you have a sinusoidal signal that has a period t, and the frequency of that is simply 1 over t, or t is equal to 1 over f, which represents the number of periods in 1 second, right? So again, a point that was made this morning with respect to vibration is that if we've got a source creating sound, some oscillatory action that is generating the sound field, then the sound is going to be the same frequency as the source, right? And so this is very characteristic of forced vibration and forced acoustics, where we have some generating mechanism that has some frequency component to it, and it generates sound at the same frequency as the source is vibrating. And that's, again, a very powerful tool from a diagnosis point of view, because if you understand what the frequency of the sound is, that can tell you what the frequency of the source mechanism is, and perhaps from some physical argument you can tell what is creating the sound. So the picture I showed you a moment ago, this is a function of time, right? So this is as if we have a plane wave propagating past a microphone at this point, and we're simply plotting the pressure as a function of time. But now, since we are powerful acoustics people, we can freeze the sound field at one particular point in time. So you can imagine this wave propagating by, we tell it to stop, and then move the microphone along through space. And we see actually the same kind of thing. We see a sinusoidal signal with respect to position, at least in a free field, where the period, the spatial period, is now one wavelength. And the pattern moves, of course, one wavelength in one period. It's traveling at this speed of sound c. And this spatial frequency, I'm not sure how much we will need to know this, but the spatial frequency is something referred to as the wave number, right? Which tells you, which is in radians per meter, and tells you the rate of change of phase with position. So if you go through 2 pi here, you cover one wavelength of the sound. So if you know the wave number, which tells you how quickly the pattern is repeating itself in space, as well as the frequency, you basically know everything you need to know about the propagating wave. And once again, total pressure is something like this, a little wiggle on top of ambient. But the microphones that we use have things referred to as pressure equalization ports, so that they are sensitive only to the small fluctuating part of the signal. In the same way that our ears are sensitive only to the fluctuating component, because we have our own pressure equalization system that balances the ambient pressure on the outside and then in the middle ear, and that device is what's our pressure equalization system? Do you know this? So the cochlea is the inner ear, right? But the eustachian tubes, right, which connect the middle ear to the throat, allows the pressure equalization to occur between the inside and outside. So we're essentially just looking at fluctuating pressure at the ear. But when it comes to quantifying levels, quantifying sound pressure levels, it's convenient to look at things that are averaged over some period of time rather than a rapidly fluctuating quantity. So most often we look at sound pressure levels or sound pressures in terms of a mean square pressure, where we take the oscillatory part of the pressure, square it, and then average it to give us the mean square pressure here, which we can then turn into a decibel value if we want, right? So that allows us to come up with a single number that tells us what the level of sound is. And this is, for example, what sound level meters give us. I don't know if any of you have sound level meter apps on your phones, of course, right? But there are amazing apps that you can get. Signal Scope is one that I'm familiar with that allow you to do more or less accurate measurements of sound pressure level just with your phone these days, right? These are, I'm showing my age here, but 20 years ago you would pay $50,000 for these things, and they're now available for $50, right? So it's a little bit of a breakthrough in terms of accessibility. So the good, I'm glad I got the spelling right. It was a great, anyway. The other thing that we're concerned with, when sound propagates through air, of course, it's moving fluid back and forth as the sound propagates. And this is referred to as the particle velocity, the actual motion of the medium that accompanies the pressure fluctuations. And this is, I think, relatively easy to understand. Again, if we imagine that this is a sound pressure wave going up and down here as a function of position, so we have frozen this wave at one particular point in time, then if we look at this little bit here, you'll see the pressure is decreasing, right, with increase in x, so that if we take a little chunk of fluid at this point, the pressure on the left-hand side of the chunk would be bigger than the pressure on the right-hand side of the chunk, and so there'd be a net force in the positive x direction, and so the fluid would be moving to the right. By the same token, in this region where the pressure is going up with position, you'd have a net force acting in the negative x direction, and so the fluid would be accelerating that way. So you can pursue arguments like this to, show that fluid is moving back and forth as a result of pressure gradients that form as the sound wave travels through space. So things are buzzing back and forth. This is also very important from a source point of view because it's vibration, oftentimes vibration of a surface that communicates itself to the acoustic medium resting on the surface and creates directly this particle velocity that then radiates as sound. So the particle velocity is a vector quantity, unlike the pressure, which is scalar, right? So that at any point in space, the pressure is independent of direction, whereas the particle velocity, of course, is associated with a motion in a particular direction. So particle velocity always has a magnitude and direction. Excuse me. So you have a sound pressure, say, looking like this, and you have a corresponding particle velocity. So the sound pressure, of course, fluctuates from positive to negative with respect to the ambient pressure, right? So dipping below ambient and above, since we can't really have negative total pressures. But the particle velocity can be plus and minus, right? So part of the time it's moving this direction, part of the time it's moving back, so we have air moving back and forth. There's, if you pursue the equations a little bit, you'll find that there's this relation between a propagating pressure disturbance and the amount of motion that is accompanying that. And that relation involves the so-called characteristic impedance, which in electrical terms is a bit like a resistance. But P over U is equal to rho naught C. As a result, if you can turn that around a bit, you get the particle velocity being the pressure divided by rho naught C. And so the question to see if you're awake after lunch is, so if you have a pressure of 1 Pascal and the characteristic impedance is 415, what's the particle velocity that results from that? So basically 1 over 415 is about 2 to 2.4 millimeters per second, right? So that and again, I would stress that 94 decibels is a relatively loud sound, but that's generating this relatively small motion of 2.4 millimeters per second, right? Excuse me. And and of course, if you decrease the sound pressure, the particle velocity goes down. And it's amazing in a way, and this is that little demonstration of 2.4 millimeters per second, and stressing, of course, that the particle velocity is obviously not the same as the speed of sound, right? Because the speed of sound refers to the rate at which waves propagate, which is 340 meters per second in normal circumstance, whereas the particle velocity, of course, is generally much smaller than that. And again, the fact that the particle velocity is very small compared to the speed of sound is one of the things that lets us get away with many simplifications, the linear acoustics assumption, amongst other things. I'll come back to something in a little while here. So we have various wave types. The examples that I was talking about earlier are plane waves, and we'll again talk a little bit about those later. But you can imagine a plane wave is something like a big sheet of glass flying through the air, where everything on a certain plane is constant at any particular moment. So it's traveling through space without changing its level. Whereas if you've got a small source, a golf ball or something that's expanding and contracting, then it's naturally going to generate spherical waves that radiate away from the source, and as illustrated here. And I think you can imagine that as the wave front gets larger and larger, the magnitude of the pressure drops again. So the sound, in a sense, becomes weaker and weaker and weaker the farther you get away from the source. You may also have cylindrical waves. You can imagine that if you had a pipe that was expanding and contracting, this would generate sort of barrel-shaped waves that would radiate away from the source. So again, they get weaker, but at a slower rate than the three-dimensional expansion of a spherical wave. So we've got those types of waves to deal with. The third quantity that I wanted to talk about for a moment is acoustic intensity, which is a power-related quantity, which again is very important to us from a measurement point of view, because it's what allows us to determine the next thing we'll talk about, which is the sound power of a source. So I think we understand that from basic mechanics, force times velocity is equal to power, right, in watts. But in acoustics, we're normally dealing with not force, but with pressure, which is the force per unit area, which multiplied by velocity gives us this, and that is commonly referred to as acoustic intensity, which you can imagine as a power flow per unit area through space. So it's a measure of the acoustic energy that's traveling through space. We can have situations where the sound pressure level is high, but the energy flows are low, and vice versa. So the intensity is quite distinct from the pressure. It means different things and can be used in different ways, and is in some sense a more robust measure of something than is the sound pressure. But again, because it involves the product of the sound pressure and the particle velocity, it itself is a vector quantity, and this again is something that's important. The intensity is a flow in a particular direction. And I would stress, sort of in normal conversation, I think we often talk about sounds being intense, right? It's simply meaning that the sound pressure is at a high level. But in the acoustics world, acoustics and noise control, intensity has a specific technical meaning, right, being this product of the pressure and the particle velocity with particular units, and so on and so forth. So we should be careful when we talk about intensity that we are specifically referring to this quantity. So the intensity that we normally deal with is this time average of the product of the sound pressure and particle velocity. And since, as I say, the velocity is a vector quantity, then the intensity is a vector quantity in the same direction as the particle velocity. And that is actually super useful for us because if a noise source is generating sound, it travels away in particular directions. And the advantage of that is that if you can reverse that, as it were, if you can trace the vector backwards, it tells you where the source is, right? So it tells you where the energy is actually being radiated from the source. And so one of the most powerful things that you can do with acoustic intensity is so-called source identification by following intensity vectors back to their origin, which again tells you where the source or where the noise is coming from, and so makes it obvious, say, if you want to reduce the noise, what region you have to deal with to achieve a certain outcome. The one simple example, if you've got a little source sitting here, I think the little source is actually missing on this slide, but you have to imagine there's a little source right at the middle of the sphere here, which is radiating sound uniformly out in all directions. So you get this nice spherical wavefront. Excuse me. And in that case, the sound power is equal to the intensity times the area, right? The intensity is outward in all directions. If you integrate up the intensity over the surface of the sphere, that gives you something we refer to as the sound power, right? And the sound power is an important quantity because in principle, it's sort of it's a fundamental quantity of the source. The analogy that we often make is that it's like the power rating of a light bulb, something that has a certain number of watts, right? And if you know what that is, you can make a prediction of the illumination in a space. In the same way, if you know what the sound power of an acoustic source is, you can use that in conjunction with information about a space to tell you what the sound pressure level is going to be anywhere in the acoustic space. It also leads to the well-known inverse square law, because if we assume that the W is independent, it's a source characteristic, so it doesn't depend on where you're measuring it, which means that the acoustic intensity is equal to the sound power divided by 4 pi r squared. So the intensity is inversely proportional to the distance squared from the source. And I would stress that that's in a so-called free field, which we will talk about more in the second lecture. So that was a particularly simple example involving something which radiates sound into a sphere. The shape of this surface doesn't really matter, so that you can have a source that radiates sound out in some arbitrary directional pattern, and still, so long as you can wrap a surface around it and do this integral of the pressure, integral of the intensity, you can work out what the sound power being generated by the source is. And there's kind of a very important corollary, I guess, to that, in the sense that if there's no source here, what does that integral add up to? 0, right? And why that is important is that, if I could remember why that's important. No. So if you have a source here, right, you can, if you want to know what the sound power of that source is, you can wrap a surface around that source and work out the sound power being generated by that source. Whereas the second source over here would contribute pressure in this space, but I think you can imagine that the intensity going into this sphere would be about the same as the intensity going out, right? So the contribution from the second source cancels, and you're left with just working out what the intensity of the sound power of the source that you are interested in. This is a very powerful result because it lets us do sound power measurements in spaces like this, right? So every acoustics lab wants to have an anechoic chamber or a reverberation room, and these things maybe cost millions of dollars and stuff. But the terrible secret is that you don't actually need these things if you use intensity, for example, to measure the sound power, because you can measure sound power in sort of arbitrary spaces like this, right? So I say to my class sometimes that you can replace money with intelligence, right? If you know what you're doing, right? So, but don't tell anyone this, right? Because from a public relations point of view, it's very important to have a nice-looking anechoic chamber and a nice reverberation room. But so this is a secret between us, I think. So as I say, the sound power is a fundamental measure of the energy, acoustic energy that a source is radiating. And it is a function of the source, right? So the sound power depends only on the source. If you know what that is, you can make important predictions, whereas the sound pressure depends on the combination of the source and the environment, and we will talk more about that later on. So just to sum up some of this, sound pressure, small pressure fluctuations around atmospheric. Particle velocity is the back and forth motion of the air that as a sound wave goes by, and is the mechanism that couples a vibrating surface to a sound field, and so causes sound generation. Intensity is a measure of the acoustic energy flow through space and is a very important tool for doing source identification and also allowing us to quantify the total sound power being generated by the source, and then the sound power, the mechanical power radiated by a source as sound. And I think I will quit at that stage. Right? So good. And we'll come back, I guess, in half an hour and talk a bit more about types of sound fields and also types of sounds. So get ready for that. Okay? Good.
stop recording.
Yeah, I think so. Yeah. So, any questions from the?
Any questions?
Yep.
The sound power can be determined by multiplying that area with intensity.
Yes.
But in free field,
In principle, from a like incremental area, right? Yeah.
in free field, I think sound pressure level is roughly equal to intensity level, like SPL equal to IL plus 0.16.
Yeah, and of course, do you know why that is? Yes. Okay. Because the way that we calculate sound pressures and sound intensity levels, the reference is chosen so that the sound pressure level and the sound intensity level are the same in a free field, right?
So, can we determine the sound power level of a source?
Sure. Yep. Okay, thank you. Excuse me. Welcome back after a refreshing break. So I want to talk a little bit more here about basic acoustics, and specifically, first of all, about the fundamentals of radiation of sound and distinguishing between planes, spherical and cylindrical waves, and then talk a little bit about signal types, whether we've got periodic things or random signals, and then something about impedance, which I'm going to use some of the local notes, I think, and then range of sound pressure levels and things. I should say, with respect to notes, let me say that the presentations that I'm using are not the ones that are included in the book, but they will be available, as I understand it, on the website soon, right? So you'll be able to get copies of the presentations that I'm using if you wish. So and I should say, speaking of presentations, that I owe a great deal to my faithful grad students who did a lot of work last week to put these together. Although the person who may be watching in Chuzhou at the moment was not involved in that process, so hello, Ray. But Tong Yang, Hyun Jun, Yu Tong, and Jia Wei, I think, were helpful in putting this all together, so thanks to them. But first of all, so radiation of sound, as I say, talking about plane waves, the classic plane waves, cylindrical waves and spherical waves, and then types of sounds. And these are, the ability to distinguish between these various wave types is important to us because it lets us make predictions about how sound travels away from the source in particular. Right, and so what it fundamentally allows us to do is to make a measurement at some point or at some location, and from that measurement predict what's going to be happening at a different distance from the source, say a larger distance. And that depends on the type of wave, so it becomes important to know what type of wave we're dealing with, and that also allows us to say something about the type of the source. So the classic division is into plane waves, cylindrical waves, and spherical waves. And the type of wave that is generated, of course, depends on the source type, physically what's causing the sound, whether it's a vibrating object, whether it's a little loudspeaker in free space, or whether it's a big vibrating surface. And then the frequency, and more particularly the scale of the frequency with respect to the size of the source, right? And then the distance that you are from the source, that has an important implication related to the type of wave you're measuring. The simplest wave, of course, the one-dimensional one that we've talked about already, is the plane wave. That travels, as I say, sort of like this sheet of glass moving through space. You have large plane surfaces over which the sound pressure at any particular moment is constant, so you can follow this wave through space. And we can generate waves like this in little tubes. Some of you have seen standing wave tubes, for example, where you have a loudspeaker at one end that's sort of acting like this piston here, vibrating back and forth, and that creates plane waves that travel back and forth through this standing wave tube. Excuse me. And the important part, the acoustic properties are constant across a duct cross-section at any particular moment, right? And of course, the sound pressure, you can, nice sinusoidal thing if we've got a perfectly periodic signal being generated by the piston. The important things about a plane wave is, as it mentioned here, the wavefront remains plane, and so in the absence of any dissipation in space, the amplitude of the wave stays the same regardless of how far you are from the source, right? So there's no attenuation with distance. And this is what we experience, for example, in ducts, right, where waves are confined so that they travel as plane waves, and essentially they can go long distances without attenuating. As mentioned here in one example, exhaust pipes in cars, we can do this kind of one-dimensional plane wave analysis. In practice, of course, let me say this, that it's easy to generate plane waves in a duct, but in a free space situation, it's not so easy, right? They're very difficult. But if you take a look at any textbook on acoustics, of course, there are pages and pages and pages and pages of stuff related to plane waves, right? And the fundamental reason for that, we could say, is that from a mathematical point of view, you can express any sound field as a superposition of plane waves, right? And this is essentially a spatial decomposition related to Fourier transforms and so on and so forth. That as I say, if you have any sort of arbitrary source, you can represent the radiation from that source as a superposition of plane waves traveling in various directions and with various characteristics. And so the reason we spend a lot of time on plane waves from a theoretical point of view is that we can use those to assemble a sound field of any source, right? And so that's, I think, the thing that lies behind a lot of the thinking with plane waves, right? So that's sort of an aside, but that justifies some of the attention to plane waves. The example that's shown here, of course, is just this little piston moving back and forth in a duct that creates a sound pressure that varies with time at any particular point. So if we have a microphone here, and we have two microphone number ones, I see. That's okay. Well, you'll have to imagine this is microphone number 2 here. And so the sound pressure at microphone 2 is the same magnitude as at pressure, or microphone 1, but there's a phase shift, of course, due to the propagation delay going from microphone 1 to microphone 2. But the important thing, the mean square pressure at microphone 2 is the same as the mean square pressure at microphone 1. And that is distinct from the idea of, say, a pipe radiating sound away, right? So that you have a uniform cylindrical surface that's expanding and contracting, as illustrated here. And in that case, I think it makes sense that you generate cylindrical wave fronts. This is a cross-sectional view, but they're expanding in 3 dimensions. And the surface area of that wave front, I think, as you know, goes up with radius, right? And so it turns out then that the sound pressure is proportional to 1 over the square root of r when you're in the far field here. And as a result, if you have these cylindrical waves propagating away, if you measure at microphone 1 and then microphone 2, you find that there's still a phase shift because there's the delay propagating from one microphone to another, but the additional thing that's happening is that the amplitude is decreasing the farther you get away from the source, right? So that is, and the mean square pressure is proportional to 1 over the square root of r. In fact, cylindrical waves are a little bit more difficult, should we say, than is indicated here, because the fundamental solution, do you know, if you solve for the simple case of a uniform expansion and contraction of a cylindrical source, The wave functions are actually what? Does anyone have experience with this? So it's actually, you end up expressing the solution in terms of cylindrical Hankel functions, right? Which in the far field, the pressure reduction relates to 1 over the square root of R, whereas in the near field it's a little bit more complicated than that. So that's why we say that the pressure is proportional to 1 over the square root of R. But in the far field, if you're away from the source, going from 1 meter to 4 meters, the mean square pressure drops by a factor of 2. So this is relevant for sound propagation from piping systems, as I say. On a slightly larger scale, submarines are kind of cylindrical objects, and we can take a look at some of the sound radiation from them in terms of these kind of functions. Jet exhaust is basically sort of cylindrical close to the exit of the jet, although diverging a little bit. So to some extent we can model that as being a cylindrical wave. And then interestingly, if you've got traffic flowing along a major highway, the sound radiation from the highway as you move away tends to follow a cylindrical characteristic rather than a spherical one, right? So that you get a slower rate of attenuation than you might imagine because of the sort of string-like nature of the many vehicles going by and creating the sound field. So the next obvious one, of course, is the spherical radiation case, where we've got, again, you can imagine now a three-dimensional sphere, a golf ball, something, or in where I come from in Indiana, the classic spherical source is the basketball, right? Very important in the Midwest. But you have an expansion and contraction of the sphere. You get nice spherical waves radiating away from the source. Excuse me. And again, following an argument related to the area of the wavefronts, you can show that the mean square pressure is following a 1 over R dependence. So if you double the distance from the source, now you cut the sound pressure level in half, or the sound pressure in half, right, rather than the cylindrical case. Speaking of basketballs, one of my guys is working on predicting the noise that a basketball makes when it hits the floor at the moment, which involves finite element modeling of the interior space as well as the exterior shell, and then coupling that to a battery element model for the sound radiation. But we hope to produce an accurate version of the ping that a basketball makes, right? But again, that's a secret project. So the things that make spherical radiation, I was talking with Manish in the break, are, of course, small sources. So anything that's small compared to a wavelength may create spherical radiation. In architectural acoustics, sometimes we build models of interior spaces at a model scale, so maybe an 1/8 or 16th scale, and sometimes sparks are used as the noise sources to create point sources to represent a source in a sound field. I have a fair bit of experience with that. And then the voice, actually, at relatively low frequencies, acts like a nice spherical source, excuse me, as well as the exhaust pipe, the termination of an exhaust pipe on a vehicle typically will radiate sound more or less uniformly in all directions. So the concept of a point source, a source that is small compared to a wavelength, and radiating spherical waves. You've probably done this exercise yourself, but you should probably start thinking in terms of wavelengths at particular frequencies to get some sense of what's big and what's not, right? So at 100 hertz, of course, the wavelength is 3.4 meters, or in in English units, that would be about 10 feet, right? But, so about 3.4 meters, which of course is longer than I can demonstrate here. But that means that the wavelength is pretty big compared to any source that's sort of handful size. Whereas at 10 kilohertz, you know, the wavelength is down to 0.034 meters. I think there's a misprint there. So actually just 3.4 centimeters, of course. So that now a source that's this size is actually many wavelengths big at 10 kilohertz. And that has a very important impact on the directional characteristics of the source. So it's useful to sort of keep thinking in terms of the scale of the wave compared to the source when thinking about the directional characteristics. So just to summarize this little discussion, the plane wave is, these are meant to be sketches of sound pressure versus distance away from a source. The plane wave, independent of distance, the cylindrical source proportional to 1 over a square root of r, and the spherical decaying faster, 1 over r. And as I mentioned earlier on, the important thing about this is that if you understand that the sound radiation from a particular source is cylindrical, then you only need to measure at one location, right, to tell you to work out what the nature of the sound field is at any distance from the source. Again, if you know that it's a spherical wave, you can just measure at one point and make a prediction at any other distance from the source. So that is kind of a powerful tool when it comes to doing things like predicting how loud traffic noise or train noise or something is going to be some distance away from the road, because you can measure at some fixed distance and then use that information in combination with the wave type to predict what the sound pressure will be at some distance where people are living, for example. And I should say that if you need to determine what type of source you're dealing with, you can do a measurement of sound pressure versus distance and see what kind of characteristic the sound pressure is following, right? And if it's following one or the other of these, then you can make these kind of characterizations and predictions. So carrying on with this discussion, in a sense, largely has to do with the terminology of acoustics, right, and coming up with a language that we can use to describe various aspects of sound. So plane waves, spherical waves, cylindrical waves, but the other terminology has to do with the type of the sound field itself in a particular space. And a kind of ideal case is this free field propagation, when the sound just consists of acoustic energy flowing away from the source into, let's imagine, a big infinite empty space, right? So there are no reflections coming from anywhere else. So no reflections, all sound comes directly from the source. And we'll talk about this, but several wavelengths away from the source. So if you are in this situation where the sound is just propagating away from the source with no reflections, then there are very simple relations between the pressure and the particle velocity. I mentioned earlier that the ratio of sound pressure to particle velocity is the characteristic impedance. So this number 415, for example. And also that if you're in a free field, there's a very simple relation between the mean square pressure and the acoustic intensity, right? Which is the reason, as I mentioned, that we build anechoic chambers so that we can create a free field environment which makes certain types of measurements easy. In contrast to the far field, then logically, the near field is the sound field that's very close to the source. And if the source has some sort of complicated surface motion, the sound field needs to follow that motion close to the source, but then it begins to simplify as it moves farther away. So typically, very close to some sort of arbitrary source, you get a kind of complicated distribution of pressure that gradually smooths out the farther you go away, right? So the near field, a region close to an extended source where the pressure and velocity are not necessarily in phase, and the wavelengths, and the wavefronts have complicated shapes. So technically, close to a source, you generate something referred to as evanescent waves. These are waves that decay exponentially with distance away from the source. Those types of waves are responsible, in a sense, for creating very fine detail, but as you move away, they gradually fade away, and you're left with a much smoother wavefront in the far field. So when the distance away from the source is several wavelengths, then you are in the far field, and if there are no reflections, then you're also in the free field. This has itself kind of important implications related to measurements of a source, because if you make a measurement very close to the source, then the sound pressure may be varying very quickly with position. And if you just make one measurement, it may not give you a representative view of what the source is doing, right? Whereas as you move a little bit farther away, it becomes easier to measure just a few points and infer what the source is looking like from a sound radiation point of view. So far field of a source is, in contrast, several wavelengths away, and the free field equals far field plus absence of reflections. And I guess I'm repeating myself here, but in that situation, the intensity is equal to the mean square pressure over the characteristic impedance. And because of the choice of reference in the sound pressure level and sound intensity level calculation, numerically the sound pressure level and the sound intensity level are the same in a free field situation. Okay, so that's various types of sound fields: planes, cylindrical, spherical, far field, near field, da-da-da-da-da-da. As far as types of sounds goes, what this is really referring to is frequency content and the nature of the sound. Of course, a fundamental description of the sound is what frequencies go together to make up this sound. I think you're aware of the idea that, according to Fourier, that if you've got some arbitrary time history, that you can express that as a sum of single frequency components, which, when you add them all up, give you that arbitrary shape, right? So that idea lets you determine the frequency content of a signal by doing a Fourier decomposition, and that is important. First of all, because the human hearing system is frequency dependent. We're very sensitive to some frequencies, we aren't sensitive to others, and so it's important to know what the frequency content of a noise source is. But also, from a noise source identification point of view, if you know what the frequency content of a disturbing noise is, you can often associate that with some mechanical aspect of a noise source that's creating the sound, right? So it may be that there's some element that's reciprocating at a particular frequency, and if you can identify that in the sound field, then it's obvious that you need to control that mechanism if you want to bring the source or the noise down, right? So why do we measure signals? To tell you something about the noise source, the identification of the type of sound may suggest the type of the source, right? So the simplest sound field, of course, is one that's periodic, a sound field that repeats itself identically every t seconds. Bless you, right? And the periodic signals, as I say, are typically generated by rotating machinery. So compressors, fans, blowers, electric motors, any device that features rotation or reciprocation at a particular constant rate is going to produce periodic or nearly periodic signals. The simplest one being, of course, something that generates sinusoidal variations, in which case there's just a single frequency, right, which is simply 1 over the period there. But in truth, more often you have a general periodic sound that consists of a superposition of something at the fundamental frequency, say 100 hertz, something at the second harmonic, twice that, 200 hertz, something at the third harmonic at 300 hertz, and so on and so forth. So all of the frequency components being integer multiples of the fundamental. So if you've got something that's periodic but a complicated shape, you can express it as a combination of F1, F2, F3, and so on and so forth, right? And again, those frequency components add up easily because of the linearity assumption that we make in acoustics and the fact that the sound pressures are relatively small. So just a classic example here, that if you add up various frequency components, you gradually, this is the Fourier series representation of, again, missing a parenthesis, but the Fourier series representation of a square wave, which gets progressively more accurate as the number of terms increases. So one subtlety here, does this representation ever approach the perfect square wave? We'll look to the students here. Okay, so it doesn't, and why does it not? So you end up with sort of overshoot and ripple at the edges, which is Gibbs phenomenon, right? But do you know why that? So that impacts a square wave, but if this were smooth, it would actually approach an exact representation. And do you know what the difference is? Right, okay, so the Fourier series allows you to express a so-called single-valued function exactly, right? But a square wave is kind of a bad example because it's not single-valued because of the jump, the discontinuity at this point. So, but anyway, that's a bit of a diversion, but you can express any kind of wave front or wave in terms of different frequency components. And then if you plot the strength of the frequency components, you end up with a spectrum, right? So energy versus frequency, that again tells you something about the complexity of the signal or the nature of the source. So sound produced by mechanical devices rotating at constant speeds are typically harmonic in this way. And Hyunjun put in this helicopter for no particular reason, I think, but it looks nice, right? Okay. The other classic type of sound, which is produced typically by aerodynamic sources, so a sort of kind of sound, is random noise, one that doesn't ever repeat itself exactly. So sound that is non-periodic, does not repeat itself, is statistically independent from one moment to another. the classics being jet noise or various noises produced by turbulent flows or turbulent interaction with solid surfaces, right? So this figure is just an attempt to come up with a random-looking sound field. And the important difference between this type of signal and the periodic signal that we talked about a moment ago is that this random signal has energy content continuously as a function of frequency, so that at any frequency you look at, there's going to be some acoustic energy, whereas in the case of something that's purely periodic, there are big gaps, as it were, between each harmonic. So there's essentially, in principle, no energy content between F1 and F2, nothing between F2 and F3, whereas if we look at the energy content versus frequency for a random signal, we have a smooth distribution of energy at all frequencies, right? And so a special type of random noise is, of course, white noise, which is defined as having equal energy per hertz, right? So at any frequency, the energy level is the same. I don't have this here, but another type of noise is pink noise. Does anybody know what pink noise is as opposed to white noise?
Reduces with
so from this point of view, if you look at it from a constant bandwidth point of view, it goes down with frequency. Right, and so the result is that in a proportional band analysis, then it's flat, right? So that you have the same amount of energy in a third octave band or in all of the octave bands. So there are various colors, right? There's reddish noise and stuff like that, but anyway, classic white and pink. So usually machinery noise has both random and periodic components. If you look at the noise produced, one of the very first projects I ever did from noise control was looking at vacuum cleaner noise, right? A canister vacuum cleaner for Whirlpool in the U.S. So of course there's centrifugal blower in the canister that sucks air through the system. There's also on the floor unit, there's a rotating, at that time, beater bar that's supposed to bounce dirt up off the carpet that's then sucked into this thing, right? So you have a combination of periodic things related to the beater bar and the centrifugal blower, but because of the air motion through the device, there's broadband random noise as well. And so it's important to distinguish between those various components to figure out which of the components you actually need to address. And we produced a muffler that fit inside the canister. We did isolation for the beater bar and produced a vacuum cleaner that was really quiet. And the disappointing thing was that Whirlpool then stopped making vacuum cleaners. So it's like, oh, okay, well, that's fine. But anyway, so I'm going to switch a little bit at this point and bring up this. So using our local notes here, I just wanted to emphasize a couple of things. The range of sound pressures that we commonly experience are illustrated here, from extremely loud sounds that are like 100 pascals or so down to things that are, say, 1 times 10 to the minus 5 pascals. So there's at least a 7 order of magnitude range that the humans can experience in terms of sound pressures. which, as I say, is very impressive from a transduction point of view. The hearing system works over that range. And the point of course, acousticians want to turn everything into decibels, right? And the point of that, at least the traditional justification for this, is that it compresses this numerical range that's going from 100 down to 0.0001 into a much smaller range of numbers that's easier to deal with, right? So the decibel calculation involves typically a ratio of a quantity to a reference quantity, 20 log root mean square pressure divided by a reference root mean square pressure, with respect, and that reference pressure is usually 20 micropascals when we're dealing with sound in air. And again, the question for 2 points on a short answer exam is what's the significance of 20 micropascals? Does anyone? Well, by the fact that we're choosing that as the reference pressure, it, of course, is 0 decibels, but why do we choose? Okay, yeah, so it's the threshold, it's the sort of minimum sound pressure that, as it says in the textbooks, a healthy young adult, right, can hear at what frequency?
1 kilohertz.
Yeah, about 1 kilohertz or so, right? So, and the choice of that reference, so if that's the lowest sound pressure we can hear, when you do this calculation, it means anything that we can hear is a positive number in terms of sound pressure levels, right? So a range of sound pressure levels from 0, when you've got a 20 micropascal root mean square pressure, up to, say, 124, which corresponds to this 31.7 decibels. So we're looking at numbers that run from 0 to 120 or something, which is arguably a more manageable range of numbers than 7 orders of magnitude. I will say, if you keep your eye on the literature related to this, there is a resistance movement at the moment who think that decibels are a bad idea, right, and think that we should be working in terms of pressures all the time. But for the moment, they are not the majority. Right? The other advantage of decibels from a human perception point of view is that the scale of decibels corresponds very roughly to our human sensation. Right, so that, excuse me, the way that this works is that if you double the mean square pressure, right, if you double the mean square pressure, the sound pressure level goes up by a factor of, by 10 decibels, right? And that corresponds roughly to a doubling of our sensation of loudness, right, which is a subjective experience, something that you can try at home with an audio device. You can conduct experiments yourself. You can ask, if you've got something playing music, you can ask someone to double the sound level, right? And if you conduct enough experiments, what you find is that people adjust it up by about 10 decibels, right? So each 10 decibel change corresponds to a subjective impact or a subjective experience of doubling the sound pressure, right, in space. Okay, and then I just wanted to say a few more words about anechoic and reverberant spaces. I've already said that the significance of an anechoic space, so an anechoic space is one where you have sound-absorbing materials all the way around on all the surfaces of the room. so that if you have a sound source in the room, all of the outgoing sound is reflected at the walls of the room, nothing comes back. And so that is creating our nice free field situation where the sound is just radiating uniformly away from the source. And so we have these very simple relations between the various acoustic quantities, pressure and particle velocity. And that means, for example, that we can measure sound power in a room like this if we measure at enough locations around the source. On the other hand, we have the other classic space, which is a reverberant space, where all of the interior surfaces in the room are hard, right? Which means that we have essentially perfect reflections from all the spaces, or all the surfaces in the room. So what that means is that if we generate a sound, it bounces off all the many surfaces in the room, and everywhere in the room they add up to give a more or less uniform sound pressure in the space, right? So in principle, in a perfect diffuse reverberant space, the sound pressure is independent of position away from the source, right? It does not depend on distance because of all the reflections. And again, that means that there's a very simple relation between the mean square pressure that you can measure with a microphone and energy-related quantities. So if it makes the measurement of total sound power of a source kind of easy, because you can put a machine in the reverberant space, let it run, and with a very simple calculation based in principle on a single measurement, you can work out what the sound power of the source is, right? So that's kind of the justification for building reverberation rooms and things like that, and used for many other purposes as well, but that's the original thinking. What this figure is a very nice figure that is illustrating the dependence on sound of the sound pressure level with distance away from a source in a kind of confined space, right? Because as you move away from the source, this source is the sound pressure may be going up and down because of the near field effects, but gradually the near field effects wear or attenuate, and you're left with a reasonably smooth decay in what appears to be a free field situation. But then if you get far enough away from the source, the impact of all of the reflections become very important, and they start adding up and flattening out the sound pressure level, right? So, and this has very important implications from a noise control point of view, because the level out here, far enough away from the source, is determined by the reflections from all of the hard surfaces, right? So if you want to reduce the sound pressure at this distance from the source, what do? You put absorbing treatments on the various hard surfaces, and that reduces the sound pressure level when you're far from the source. But if you were in this region, essentially putting absorbent surfaces on the wall doesn't do anything for you, right? So that would be a waste of money if you were to put absorbent material all over the interior space, because that would not really affect the sound pressure level at this point. So if you wanted to reduce the sound pressure at this point, what would you do? Yeah, so the obvious answer is that you'd put the source inside a box or something, right, to prevent it from radiating into the space. So this business of knowing how the sound pressure level changes with distance away from the source is very important from many points of view, but suggesting what the treatment should be. So in that little example, the direct field, some more terminology, is the field that's radiating more or less directly from the source as if you were in a free field. And then the reverberant field is the sound pressure out here, which is largely determined by all the reflections from the interior surfaces of this space. And one final thing on this front is that if you have sound hitting a hard surface, so we'll have this little discussion of, say, a plane wave comes along and hits the surface, what happens next? It reflects, right? So there's a zero normal velocity boundary condition at the surface, the sound reflects in phase. So what's the total pressure at the surface? The sum of the direct wave and the reflected wave coming back off the surface. And if it's a perfectly hard surface, then it's the reflected wave is the same strength as the incident wave. So the pressure here at the surface is twice the pressure of the incident sound field coming down, right? And so if you work out the math on that, that means that the sound pressure level at the surface is 6 decibels higher than the sound field in free space before it interacts with the surface. And again, that has kind of practical consequences, because if you want to know something about the source, you're really interested in the free field radiation away from the source. But if you put your microphone too close to a hard surface, you get this pressure amplification, which means that the sound pressure level will be higher than it would be in free space. And so you're maybe not getting accurate information about the source in that instance. Just as a matter of interest, then, if we do have a wave of strength 1 coming down and hitting the surface here, the strength of the reflected wave is 1 coming back. But what is the strength of the transmitted wave? No.
In the hard surface, right?
Yeah, because at a surface like this, what are the boundary conditions?
V is equal to 0.
Right, and so if this is medium 1 and the table is medium 2, the pressure has to be continuous, right? At the surface, right? So the pressure at the surface is equal to 2, and so the transmitted pressure is twice as high as the incident pressure, right? And so that seems strange, right? The transmitted pressure is a little higher than the incident pressure, but if you actually work out the energy involved, very little energy is being transmitted.
Because of the difference in the characteristic.
It's exactly due to the difference in the characteristic impedance. So you get relatively, so this is like transmission from air into water. You can actually get quite a, and yeah. So the pressure can be high, but the energy is small because of the big difference in characteristic impedance then, right? So anyway, that's a little bit beside the point. But I think, on the other thing, just from a terminology point of view, if I'm right. I just wanted to say a few words about impedance, because impedance is something that comes up all the time in various ways. The impedance generally is the ratio of a force quantity to a velocity quantity, right? And tells you something about how much force you have to exert on an object to create a certain amount of motion. And it would be simple in the acoustics world if there was only one type of impedance, but for various reasons there are multiple types of impedances, which leads to all sorts of confusion. And and we often refer to the fact that many years ago, was it NASA that their satellite, the probe that was supposed to orbit Mars actually crashed into Mars because some of the calculations were done in metric units and some were done in feet, and they didn't quite keep them separate, right? So we talk about these kind of things in the same kind of terms, because if you use the wrong impedance in the wrong context, then you can crash into Mars, right? But the mechanical impedance, which is often used to characterize mechanical vibration, of course, is a ratio of a total force to the velocity at the point that you're driving. Whereas specific acoustic impedance is a force per unit area related to a particle velocity, which is then pressure divided by particle velocity. And just to confuse the situation further, something that's called the acoustic impedance is a ratio of a force per unit area, sound pressure, divided by a volume velocity, which is a velocity times a cross-sectional area. This kind of impedance is very useful in duct systems because the acoustic impedance is continuous at discontinuities or joints or branches in a duct, whereas the specific acoustic impedance, you'll note that there's no area here. So this is essentially a per unit area calculation. So if you've got big surfaces, big plane surfaces, then this is the kind of impedance that we often use. Whereas if we're dealing with sound radiation from maybe a baffled piston, we're talking about the force that's applied to the sound field divided by the velocity. So all of these impedances are very useful when talking about source and surface characteristics, but the message here perhaps is that it's important to keep in mind which one you should be dealing with at any particular time. And I think I will quit at that stage. And so, if we kill the video, we can take any questions from the crowd, right? How long will it take?
Yeah, we can ask questions.
Yeah. So does anybody have any questions? Make me work for a living here. Well, I'll throw in one thing. So something that I mentioned earlier was the idea that you can express any kind of sound field in terms of a superposition of plane waves, right? And so plane wave analysis is kind of important from that point of view. There is a measurement procedure that is based on that idea, right? So the acoustic holography stuff that I'll talk a little bit about on Friday, I think, is a very powerful procedure that involves measuring the sound pressure on a surface above a source and then doing this so-called plane wave decomposition, which allows you to project the sound field back towards the source, one component at a time, in a sense, and then reassemble at the source location, so you can get a very detailed acoustic image of what the source looks like, right? So you get very graphic representations of the source. But that, as I say, a very powerful procedure from a noise source visualization and identification point of view, which is made possible by the fact that you can do this plane wave decomposition and express any kind of sound field in terms of its plane wave components.
Measurement done in the near
Yeah, so the measurement typically is done in the near field where you have access to both the propagating components and then the evanescent components that I was talking about earlier, which give you the very fine details of the source. Right. Good. So
when we are calculating the, like computationally calculating the far field noise,
yep.
the near field and far field demarcation depends upon the frequency. So when
Yep.
we are talking about, say, I want to talk about far field noise, and then I have a range of, say, 100 hertz to 4 kilohertz.
Yes.
So how do I stand with that? Say my source is a point source, but then
Yep.
say I'm talking about because
Well, if it's truly a point source, then there may not be much of a near field, regardless of frequency. But it's more an issue if there's some extent to the source, right? Because then the near field is clearly going to be a function of frequency, right? Because you really want to be a few wavelengths away from the source. To mark the transition from near field to far field. But also if the scale of it gets complicated, because if the scale of the source is kind of big, then at high frequencies you get a pretty complicated distribution of sound pressure until you're out some distance away. So it's hard actually to make generalizations with respect to frequency, except if you've got a really compact source. Then you can say, of course, that the near field decays rapidly, and so you get into the far field fairly quickly, right? And that depends on how far you are in terms of wavelengths. Right?
if I have a distributed source,
then all bets are off, right? Yeah. So, because if you've got something like an engine, you know, a 6-cylinder engine,
or maybe say a fan.
sure, then the sound field is going to be relatively complicated, even at significant distances from the source.
Normally they represent, for example, far field, and you're talking about broadband.
Uh-huh.
Broadband, we are concerned with, say, 100 to 4 kilohertz. Then we
Yep.
go into they usually don't go into the details of like where did they decide the far field.
Mm-hmm.
Talk easily about far field.
Yeah, well, so you should, right? So, because all of these things, the scale depends on frequency and right? So, you need to be conscious of where the transition is from one to another as a function of frequency, right? Because you can get into trouble, as I say, if you think, you know, you're in the far field and you're measuring at a particular point, then you want to extrapolate farther away. If you're not really in the far field, then it's going to be very inaccurate, right? Okay, I think we can quit at that point. Thank you.